So it was kind of difficult to find practice problems on randomization and approximation algorithms, just because when I took the course, we didn't go over it in that much depth, and similarly, when Anka taught the course last semester, there was only a limited amount of materials on it. But we'll do our best. So yeah. Oh, also, we'll definitely plan to take a break, because 3 hours of continuous review is a lot. And if we finish before the 3 hours, I'll just use the rest of the time as like an office hour period where you can ask me questions. Sound good? Okay. So the final's on Tuesday. I hope you've been aware of that. You've been studying accordingly. It's at 9 a.m., unfortunately. It's also in Barton. And I think make sure you're in the right room when you take the final, or there's like a 10% penalty, something like that. The exam is cumulative. So, I mean, when we say cumulative, it's like pretty evenly distributed, except there might be like a slight emphasis on topics since prelim 2, as in like, there will definitely be problems that test you on material covered since 2. There may or may not be problems that test you on content from prelim 1 and prelim 2. Does that make sense? Do you have 2 hours or 2.5? Or 2.5 might be long. 2.5. 2.5? Okay, 2.5. So that's kind of a lifetime to finish the exam. So hopefully you feel less rushed than you do on the prelims. And as in the prelims, you should expect to see kind of a mix of like short answer and then some longer free response problems. Yeah, we'll fix it in a second. So the same ed post that I wrote before the first prelim, I think all of this stuff still applies. So if you need a refresher on like some good test taking strategies, please go read that. Try to get as much partial credit as you possibly can. I think you've seen enough of our grading and feedback over the course of the semester to hopefully have a good idea of what it is that we're looking for. Read the questions really carefully, right? Some of them can be more complex, especially those longer ones. And you may have noticed either on the prelim or on some of the homeworks, if you make the wrong assumption, you're kind of screwed, right? So you have to be really careful about like what you assume given the problem statement. To that end, review the homework solutions to make sure that you can follow along the thought process that they've been going through. Sleep, if you're up until 4 a.m. and trying to cram before a 9 a.m. final, I promise you it will not go well, no matter how much you were able to study. And then be wary of your timing, right? So like, yeah, 2.5 hours goes by pretty fast, even though it is more time than you get on. So these are the topics that people wanted to review the most, and then after all of these topics, I have a couple more practice problems for us. So we're going to start with approximation algorithms, then we'll talk about randomized algorithms, computability theory, dynamic programming, and NP completeness. We might switch the order around a little bit because Kira needs to go a bit early. So we might do DP right after approximation algorithms, if that's okay. Yeah, let's get started.
Okay. Okay, so approximation algorithms. First, we wanted to kind of give an intuition as to why we use approximation algorithms in general. So in some situations, just finding some sort of approximate solution where we know it's going to be under some sort of optimization bound is good enough for us, especially in the case of NP hard problems. Finding an approximation algorithm allows us to have an algorithm where we know the specifics of the runtime, or not the runtime, the specifics of how good it is compared to an optimal solution. And so that's why those are useful. And it's also good when we lack a little bit of information regarding the problem. That's just some intuition as to why we use them in general. Okay, so maximization and minimization problems, they're a little bit different. So if we're using a maximization problem, it's kind of intuitive that we want our approximation algorithm to be at least half the optimal. And so the way we can show this is by multiplying the approximation algorithm. Sorry, what is that Greek letter again? Alpha, sorry. We're going to multiply the approximation algorithm by alpha, and then we know that it's going to be greater than or equal to the optimal solution. And so that's good because the optimal solution is obviously going to be the solution that maximizes whatever we're looking for. And so if we know that it's as good as, at least half when alpha is equal to 2, that's good enough for us. And then as alpha changes, it's just going to give a different bound about how good our approximation algorithm is comparatively to the optimal. And then for minimization, it's very, very similar, except for we don't want it to be at least half. We want it to be at most alpha times the optimal solution. So in this case, if alpha was equal to 2, we'd want to make sure that our approximation algorithm is at most twice the optimal solution. And that's going to make sure that we're minimizing it by some bound. Does that make sense to everybody? The intuition behind alpha in relation to the optimal solution? Cool. Okay, so we're going to go through an example really quickly because I think that's the best way to kind of get used to approximation algorithms. So given an undirected graph, G equals VE vertices and edges, find a vertex set C that's a subset of V that contains an endpoint on each edge and uses as few vertices as possible. So it's basically asking you for each edge, you want to create some subset of C vertices such that each edge has an endpoint inside of C. And then, so we have does anyone want to just quickly tell me what the simple greedy algorithm would be for this problem?
Did you guys cover this in lecture?
No? I mean, they probably could have figured it out anyways, but, well, all right. Okay, so this is the algorithm. So basically, you're just going to keep picking an edge, and then add those endpoints to C. And then delete every edge that's incident, which means it's connected to those endpoints U or V. That's the greedy solution. You guys probably could have gotten there eventually. Okay, and then you return C. Okay, so now we need to actually prove that. Wait, can you go back to the question? Yeah. Okay, now we need to prove that it's giving us a 2 approximation. So is this a minimization or a maximization problem? Oh, it said right there. Okay, it's a minimization problem. So because we know it's minimization, can somebody tell me what we're trying to show here in terms of alpha algorithm and then the optimal solution, what we just went over in the last slide? Yep.
The size of our set is at most 2 times the size of the optimal solution.
Yep, sounds good. Did everybody hear that? We want to make sure that whatever set we pick, so C is going to be, oh, okay, it's on there too. Sorry. I thought that wasn't on there, but yeah, okay. Basically, whatever's up here, that's what we want to show. Okay, let's move on. Okay, so this is a very clear example as to why greedy is clearly not the most optimal solution. So say we just have 2 vertices. The way our algorithm is going to work is going to take this edge, pick U and V, and add both of those to C, when the optimal solution really just to be to add one of them. And so that's like a very intuitive way of seeing how greedy is at most twice the optimal solution, right? The optimal solution picks 1, a subset of size 1, and the greedy solution picks a subset of size 2. So that's an intuitive way to look at how it's twice the size of the optimal solution. Oh, this is another one. Okay. So I can talk a little bit about how you would just prove. Does anybody want to tell me about how they might prove that last problem? We didn't put a proof on here, but based on your experience with approximation algorithms, how might you be able to generalize this one example? So we have an example that's very clearly showing us that it's twice the optimal solution. How would you be able to generalize this into proving that for all cases, our greedy algorithm is always going to be at most 2 times optimal solution? Yep.
You could consider some like arbitrary optimal solution, and for that, you know that for each edge, there's going to be at least 2 vertexes at like maximum that are in the independent set. But it doesn't necessarily need to be 2. Like you could have 1 in the independent set. And so from that, you know that like if there's only in the optimal solution, an edge only has 1 of its vertices in the solution, and you have 2 of the vertices in our solution. That means we're gonna have a maximum of 2 times the amount of vertices.
Yeah, so that's kind of the right track-ish. So what you did is very important, which is you defined the optimal solution in terms of the problem, and then how our algorithm would work comparatively to that. So that's kind of how you can start to go about proving approximation algorithms. You're going to want to find some property or some description of the optimal solution in terms of our original problem. So you might say if we have n, or we have v vertices, you might want to try to find a way to define the optimal solution in terms of that, and then also try to define what we know about our greedy algorithm in terms of the same the same variables. And then that way you're going to be able to actually take that equation that we saw earlier with alpha, put in your definitions for the optimal solution and the approximation or your greedy algorithm solution, and then be able to simplify that eventually to get some sort of bound, which we're going to do in the next problem. So we can go to the next problem now. All right, so this is similar to a problem that we did earlier. I think it was review session 1, but it's a little bit different. So you have n containers of weight wi or w1 to wn. You also have a set of trucks, and each truck can hold k amount of weight, and you're going to load the trucks sequentially. So in order of w1, w2, etc. You want to minimize the number of trucks used for this. So you want to minimize the number of trucks that you need to carry all n containers, with the constraint that each truck can only carry weight k. Yep. Okay. So yeah, the greedy, I'll give it to you. You basically just start off with an empty truck, and then you put the containers in order that they're there until you can't fit anymore, and then you send that truck off. Does that make sense to everybody, that greedy algorithm? Okay, cool. Yeah, so clearly this is not the optimal solution. Does anyone want to give me an example of some weights where greedy would not be the best solution? Okay, we'll go to the next slide. I think there's, yeah, okay, here's an example where it's not the optimal solution, because right, what would our greedy solution do? It would put the 2 onto the first truck. If it tried to add the 3, it would be over 4, so it's going to send that truck off, then put the 3 onto the second truck, and then finally the last 2 and 1 are going to be on the last truck. So it's going to take 3 trucks when the optimal solution is only 2 trucks, right? So if we could have seen all the containers ahead of time and then pick the weights per truck ahead of time, then we'd be able to get 2 trucks. So that's the optimal solution. Okay, so we're going to give you a few minutes now where you can kind of think about how you might want to prove that this greedy algorithm is a 2 approximation. So again, this is a minimization problem. So, you want to prove that your optimal solution, or sorry, that your greedy algorithm is at most twice the optimal solution. So again, let's try to keep that in mind, and then try writing the optimal solution in terms, or try using what you know about the greedy algorithm and the optimal solution to try writing them in terms of the same variables so that you can eventually simplify it down. And we'll give you a few minutes to do that. Yeah. Oh. Which honestly, was that on here? Hello? 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 Is that getting lower or am I just unscrewing it? Or is it this one? Hello? 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 Is that? Hello? That's really loud. Yeah, that's probably fine. Hello? Hello? Oh, wait, hold on. Is that good? Good? Okay. I think I just... Oh. Okay, let's go over the solution for this one. Okay. So the first thing that we're going to do, again, is we want to define the optimal solution. And the way we're going to do that is we're going to put a lower bound on it. So we know we're going to define W as the sum of all of our weights in this. Wait, actually, should we add them to, I'm not, okay, I'm just gonna go over the solution. Oh, sorry. Okay, so you know that the optimal solution is going to use at least W over K trucks, right? Because the optimal solution would be, we have all the weights and we're able to just divide them by the weight limit K on all the trucks. And that's gonna be, so the ceiling of that is gonna be the minimum amount of trucks that we need to use. So does everyone understand why that's our lower bound on the optimal solution? Right, and we're defining our optimal solution in terms of what we already know, which is the weights and the weight limit of the truck. Okay, and now we're gonna put an upper bound on our greedy solution, and this is gonna be important later when we're. Do you remember in your homeworks when you did all that series of inequalities to get from your solution to the optimal solution? That's kind of what we're trying to do here. So we're gonna put an upper bound on our greedy solution because we want to make sure that our greedy solution is always at most 2 times the optimal solution. So if we're going to pack items sequentially, for any pair of trucks, that combined load needs to be greater than K, right? That's pretty intuitive because if it's less than K, we could have probably fit more onto the first truck and we wouldn't have needed to split them into 2 different trucks. Okay, so because we know how our greedy algorithm works, which is we pack it until it's almost full, we can put this upper bound on just like those 2 trucks that are right next to each other. And then we need to actually consider 2 different cases, which is even trucks and odd numbers of trucks. So this is kind of a complicated one. Hopefully you won't get something like this on your final. Okay, so this is our even number of trucks. Okay, so on average, right? I'm trying to think of an intuitive way to explain this. On average, every truck is going to have a load that's greater than K over 2. Does anybody want to try to like explain why that's the case? It's like on like, yep.
If there was a truck that had load less than or equal to k over 2, then there should be some kind of way to. Originally, I was thinking that there would be 2 consecutive trucks that had weight at most k over 2, which means that there's some item that doesn't tip over the limit, but then gets pushed to the next truck anyway, which is a contradiction. Although I'm not sure how to prove this for if only one truck is less than or equal to 2.
Yeah, I mean that's pretty close. So he was basically saying that so the first part of what he was saying is that if there was a truck, I can't remember the way you phrased it exactly, but yeah, if there was a truck that had like if the average was less than this, there would be a way to shift everything around such that we would be able to get less trucks using our greedy algorithm. Okay, so we have this. Yep.
Is it meant to be every truck, or is it meant to be each truck? Because there can be one truck that has less than.
Well, so it's just on average. It's not saying like every truck is going to have.
But it says on average every truck, right? Does it mean on average each truck must have a load give it in? Like average of all trucks.
Okay, I thought those were synonymous, but yes, sure, it's each truck. Okay, so we know that the total number of trucks. If we know that there's this bound now that each truck is going to have an average load of k over 2, then we can create this bound on our total number of trucks. So taking the sum of weights, we can divide it by what we see as the amount in each truck, which is w over 2. And we're able to get the fact that the number of trucks that we're using in our greedy algorithm is going to be less than 2w over k. And then you get that great line of inequalities, which should look very familiar to you, which is we take what our algorithm, the upper bound of our algorithm, which is 2w over k. So we're saying that our algorithm is going to be less than this. And then we're saying our algorithm is going to be greater than or equal to the optimal solution, right? So best case, our algorithm is equal to the optimal solution, but it's most likely not going to be because it's greedy. And then we know an upper bound on or a lower bound on our optimal solution too, right? So our optimal solution at best is going to be equal to w over k. So now you see why we need these bounds on our solution. So it's not super important that you get the exact number for each solution, but you need some sort of bounds so that you can create the series of inequalities. And then once you rewrite this using the alpha formula that we saw earlier, you just do our algorithm over the optimal algorithm, and it simplifies to 2. Which is super great and lovely because we wanted to have a 2 approximation algorithm for this problem. Yeah, so that's for even numbers of trucks, and I get to tackle odd numbers of trucks. Okay, so now consider the fact that our algorithm is going to give us 2n plus 1 trucks. So as you recall, n is the number of containers that we have. Again, so okay, the first 2n trucks are going to have a combined weight that's greater than nk. Does anybody understand why that is? Yes?
Just the same argument as the one. It's 2n is like.
Yeah. Oh, do you have a question?
How could you have more trucks?
More trucks than containers?
Like is n the number of like boxes, like the shipping boxes?
Yeah, n is the number of containers.
So then, like, if you put like.
Oh, okay, because we defined n in the problem as. Yeah, n containers, but we're just using it as an arbitrary variable now.
Oh, yes. No, but I think it's the same.
Okay, but then yeah, how can we use more trucks than containers?
I think this is.
Okay, never mind. Okay, that n is just an arbitrary variable. That makes a lot more sense. Okay, sorry. But okay, so the 2n plus 1 is an arbitrary n, and then is the nk is the number of containers. Okay, yeah. So the nk is the number. Sorry about that. That's kind of confusing. Okay. So yeah, so we're given this arbitrary n, and we have an odd number of trucks now, and so again. Because we know that the weight is going to be over nk, We know the optimal solution is going to need to have n+1 trucks, because if it had n trucks, then it wouldn't be holding all of the weight, because combined weight would be greater than nk. Yeah, okay, and then we have a similar set of inequalities. So now we just have different bounds on the optimal solution in our greedy algorithm. But again, if you just simplify it, you get 2. Does that make? Oh yeah.
Why the first 2 n trucks have combined weight greater than nk?
Yeah, so n in this case is just an arbitrary variable of like the number of trucks that we have.
The total number of trucks.
Do you want to explain that?
The total number of trucks used, you had to still pack all the items, right? Right. So your greedy algorithm, right, is packing every single item. So the combined weight of the first 2 n trucks, if you have 2 n plus 1 trucks, is at least nk, where nk is a bound on the weight.
It's just like the number n, if n is just some number, and we know we have 2 n plus 1 trucks. Like that means that the weight is going to be greater than like n times k, because n times k would be if we just took the first n trucks and multiplied it by the weight capacity on each of those, but we're not, we're taking 2 n plus 1 trucks, because that's how much we basically need for our greedy algorithm to pack all the trucks. Yeah, so the previous slide is so no, because we use a different bound on the previous slide. We're assuming that there's an even number of trucks, and I think that's why we can find that average of k over 2. When there's an odd number of trucks, it's going to be a different bound.
Very similar.
Yep. Okay. So just basic outlining of approximation algorithms, proving it. You're going to try to find an upper bound, either an upper bound or a lower bound, depending on if it's a minimization or maximization problem. Once you find those upper or lower bounds on your optimal solution and the greedy algorithm solution, you should be able to use this series of inequalities to eventually get to something that looks like this. Like your algorithm over the optimal is either greater than or less than alpha, and that's going to get you the alpha approximation. Does that make sense to everyone? Okay, we can move on. Okay, do we want to do another approximation algorithm question? Yes? Okay.
I believe this one was in your practice problem set, but again, I have very few problems on approximation algorithms to give. And so we're just going to go through this one in a lot of detail, and hopefully if you didn't understand it from the practice problem, you'll understand it now.
Yes. Okay, so this is the acyclic subgraph problem. So you're given a directed graph G, and the objective is to output a subset of edges such that the subgraph does not contain any directed cycles. And that the number of edges in E is as large as possible. Okay, yeah, so this is an NP hard problem trying to find a subset of edges that are acyclic and also large as possible. So we're going to develop an approximation algorithm for this problem. Yeah, these are just definitions of variables. Do you want to give them the algorithm, or do you want them to come up with the algorithm? Okay.
Right, so think carefully about what these definitions are, right? Specifically, EF is a set of edges such that I is less than J, where we've arbitrarily numbered our nodes, and EB is the other way around, right? And both of those sets form a partition over our set of edges. And so we're going to make one graph such that GF is equal to V and EF, and another graph such that GB is equal to V and EB. So first thing that you want to do is prove that these graphs are both acyclic.
Any ideas on how we would prove that these graphs are acyclic?
You can do contradiction. You assume that they're not acyclic, or there exists a cycle, and that means there's a way to go back to a certain node. But that would mean like that if you like took that path that there would exist an edge going in and out of that node, but that would mean that there's one that's greater than and one that's less than.
Yep, spot on. That's exactly it. So, hopefully everyone heard that. You'd prove it by contradiction. Yeah, so if you assume that there's a cycle in it, you'd eventually come to the contradiction that you can take a path back to a node that's less than, which is, less than? Yeah, which is a contradiction because that's not how we chose our graphs. Okay, so that's the first thing that you have to prove for this problem. And then the next thing that you have to prove. Okay. Yeah, so we'll give you some time. We'll give you about like 5 minutes to try to come up with some sort of skeleton algorithm for this. And because you're designing it, hopefully it should be a little bit easier to write a proof for an approximation algorithm because you're the one who's writing it. So you can hopefully make it easier for yourself, but we'll give you like 5 minutes to try to come up with an algorithm for this.
The fact we just proved was very helpful, so you should try and use that.
So, was it not what you just showed? Like, was that not the algorithm?
No, we proved the fact about the two graphs, right? We constructed two graphs. We proved some fact about them.
Okay.
Still need an algorithm that solves the problem. Right? We want to maximize the problem.
Okay. All right, we're gonna go over it now. Sorry. Okay, here's the answer. So, you know that these are complements of each other, right? So they're not going to contain all the same edges, which means that if k is the number of edges, sorry, the cardinality of each set is going to add up to k, and it's also going to be less than or equal to k over 2. So you just pick whichever one has greater number of edges, and then you output that. And because we know that they add up to k, then we know that each of them is going to, the one with the larger number of edges is going to be greater than or equal to k over 2. Sorry, not k. Any questions about how we got there? Yeah, pretty straightforward problem. Okay.
No, K is just like yeah. Right, so K would be the
Yep, okay, that's a good point. Yeah, K is the optimal solution. So we're saying that this is bounding, the optimal solution K is bounded by a factor of 1/2 to our solution. Yep,
Is it like something we could expect to be given in like the prelim? Or
the
final?
hint.
Yeah, or like was that part of the original problem or is it?
I think that was part of the original. Yeah, this was our prelim, so I think that was given to us on the prelim.
Yeah, I mean, this was on a final before, but you shouldn't like expect that you'll be handed the hints, right? To like, I don't know, the hints I think kind of gave away the algorithm in this case. You might not get a hint like that, and I think it's reasonable for you to get something like edge coloring, for example, from your homework. Like that's a difficulty of an exam problem.
Okay. I'll take a break.
Okay. So now I'm going to talk a little bit about randomized algorithms, and yeah, this is a bit of a tricky topic, especially because for the past couple semesters, randomized algorithms have only been like brushed over very briefly. So first time I found out what hashing was when you guys learned what hashing was. So that was a fun little experiment, but yeah, let's just kind of go through. I also think that the problem I came up with for this was on your practice set. I didn't realize that until like an hour ago, so that's unfortunate. But anyways, why do we use randomized algorithms, right? Let's try to motivate a little bit about why they're useful. Randomized algorithms are almost always used to improve our time or space complexity, right? It's by introducing some non-determinism into our actions, we can perform much better, right? So like quicksort, for example, the randomized quicksort algorithm is really fast because we allow it to just randomly choose a pivot. And in expectation, it works really well, right? But in the worst case, it still doesn't do super great. So it's actually an open question related to the P versus NP problem, whether or not randomization is a useful tool in solving problems efficiently. It turns out that if P does equal NP, randomization is actually not helpful, right? As in we could, it will not help us kind of narrow our search space faster. But it's not like an end-all be-all solution, right? So randomized algorithm, like on its worst input, will be no better than its parallel like deterministic algorithm. Does that make sense? So when we're analyzing randomized algorithms, naturally a good bit of like probability theory comes up. We're not going to expect you to know probability theory beyond the level of 2800, but hopefully after doing the last homework, you're comfortable with the basics of random variables, expectation, taking expectations, etc. Okay, so the problem we're going to go through today. In class, we saw a randomized median finding algorithm where the expected running time was O of n. And in this one, we're just going to look at kind of the number of comparisons we need to make to find a good pivot. So I think in class, we said that we would like a pivot in the middle half, right, of the items in the array sorted. In this case, we're okay having a pivot in the middle third, right? So instead of picking one element at random, oh wait, I think those are two different problems. Oh, I did pick a good problem. Never mind. Okay, so instead of picking one element at random, we're going to pick 3 elements at random, and we're going to choose the best one basically to be our pivot, right? So we're going to take the median of those 3 elements, and the median of the 3 elements we choose will be the pivot, and we'll compare the position of the thing that we chose to the remaining elements sampled, right? And so if we're within the half that we want it to be, right? If we're between n over 4 to 3n over 4, then we'll discard the part of the array that we know doesn't contain the last n over 4 elements, and we'll recur, right? If it's not in the middle of range, we'll try again picking a new number. Okay. This is just the median finding algorithm from class. But instead of picking like a single element and trying until we get it, we're going to pick 3 elements. We're going to pick the median of those 3 elements and hope that that brings us closer to the median at each iteration. Does that make sense? Okay, so the first thing we want to do, find the probability that the index of the median of the 3 points is between n over 4 to 3n over 4. And the second thing we want to do is state the recurrence relation for the algorithm. So this is a divide and conquer algorithm, right? It's randomized, but it is divide and conquer, so you can bound its running time using a recurrence relation, and then you can take the expected value of that recurrence relation to get an expected running time, right? That's what we're going to try and do. And we're going to show that the number of comparisons made by this method is upper bounded by some constant c, for c is less than 6. Okay, this is a bit of an gnarly problem, so I'll give you guys a couple minutes to work out some of the math. Okay, so let's kind of work through a little bit of the math. So generally, when we're finding probabilities, it's easiest to work with the complement, right? So Andy, can you go next slide? Okay. So what is the probability that we draw from one of the sides, right? Like either the left side or the right side that isn't the middle chunk, right? Well, it's a quarter on the left side and a quarter on the right side, so it's a half to draw from not the middle chunk. And so the joint probability of doing that 3 times is going to be 8, right? And the probability of drawing from the middle interval is going to be a half. And so we have 3 options from which our draws are from the middle, right? And for the other 2 draws, the probability that the first one falls outside of the middle is a half, or the probability that the other one falls to the same side is a fourth, right? So basically it is like, if the median is indeed in the middle, right, there's only a few certain permutations that will get us there, right? So it gives us a total probability of 3/16. Did anyone get that probability? That's okay. And note that these are disjoint probabilities, right? So the combined probability of not having the median be in the correct interval is going to be a probability that it falls on one of the other 2 sides, plus a probability that it doesn't always fall on one of the other 2 sides, but the median is still not in the right interval. And so that gives us 1 minus 1/8 plus 3/16, which is 5/16. Yeah?
Isn't the probability of it being on the left and the right 1/4? Or am I wrong?
Well, left or right. So the fourth for each, right? So it's a half, yeah. All right, so I think the trickier case to understand is how we got 3/16, right? Like, why is it the case that like the median itself is not in the middle part, right? And it's a chance that two of them are on one side and one of them's in the middle, right? So you'll get some kind of permutation like that, yeah. Yeah. So the probability that so we already calculated the probability that like all three of the elements that we choose fall on either the left or the right. But you could have like one element fall in the middle and the other two don't fall in the middle, right? So the 3/16 is accounting for that probability, right? So the probability of drawing from the middle interval is 1/2, and you have three options for which one of your draws is going to be from the middle. And for the other two, right, the probability that the first one falls outside of the middle is also 1/2. But the other element needs to fall to the same side of being outside on the middle for the median not to be in the middle, right? Sure. Oh. But both of them they both need to be on one side, right? Yeah. So that probability is still going to be 1/2 times 1/2 times 4, right? And we have three chances, so it's 3. So we get 3/16 for the probability, and so the total probability that the index is in the middle range is the complement of the probability that it's not in the middle range. That's 1 minus 5/16, which is 11/16. Yeah. This will be the third time then. Okay. So again, the 3/16 is accounting for the probability that one of our draws is in the middle, but the other two are not, right? Like, why does that matter, right? Because we're looking for the case when the median of the three elements, guys, can you quiet down a little bit? Okay. So we're looking for the probability that the median is not in the middle, right? Which means that two of them fall to one side and one of them might be in the middle, right? So we already accounted for the case where they both fall to the outer sides, right? So that's just 1/8. But the probability that two of them fall to one side and one of them falls in the middle, that's how we get 1/2 times 1/2 times 1/4. And we get 3 tries to make that happen. So 3 times that probability. I would maybe draw it out. Like draw a little bar and then try and convince yourself. Yeah? No. Yeah. Okay, let's go to the next part. Okay, so now we want a recurrence relation, right? So we expect to find a valid point 11/16 of the time, and we expect that on average it will take 16/11 tries to find a valid point. Where does that number come from? Yeah? Right. So the number of tries it takes for us to find basically a median being in the middle is a geometric random variable. And the expectation of that geometric random variable is just 1 over the probability of success, which is 1 over 11/16, which is 16/11, right? So in the previous method, we required n-1 comparisons. In this case, we only require 3 comparisons, right? You also need to compare the median to all of the other elements, right? Like once we find the median, then we need to compare against everything else in the array. And so that gives us a total of still n comparisons, right? It's still O of n comparisons. So we can write a recurrence relation that will give us 16/11 times n plus t of 3n/4, since we reduce the size of the problem by 3n/4. Does that make sense? Okay. Then you can do some fancy math to solve the recurrence, right? So it's just a sum. But we're allowed to evaluate it in expectation. And so it's the sum over all index j, where j is just like the index that it takes until we get to the end, of 16/11 times n. And that can be pulled out. And the sum is just going to be a geometric series like we've been seeing in recurrences all semester. And so then it's just 64/11 times n. And 64/11 is a tight upper bound, it's less than 6. Okay. Next slide. Oh, yeah. Are there questions on this? Yeah?
Do we only like move on to the next step of the algorithm once we hit something in the middle?
Yes. Once the median is in the middle. Yeah. So it's like a while loop that just goes and says like, oh, pick 3 elements at random, find the median of them, and check if that one is in the middle. How many tries does it take an expectation for us to get that? 16/11 times n. Yeah?
Have you checked the middle? Like
The middle. compared against every other element. That's why we had n-3 extra comparisons, right? Because we already compared it against the 2 elements that we selected out of the 3 that we sampled, and then you need to compare against the other n-3 elements. Yeah. The recurrence, yeah. Go back to sleep. Right. So again, we said that the expected number of tries it takes for us to find a valid point is going to be 16 over 11, based on it being a geometric random variable, right? And how many comparisons did we need to make once we actually found it, right? Or yeah, once we found a valid point, or actually no, sorry, to confirm that it's a valid point, and total comparisons, right? Because it took us 3 comparisons to choose the median of the 3 elements, and then it also takes n-3 comparisons to compare with the rest of the elements, right? So 16 over 11 times n is the expected number of comparisons that we're going to need to make, right? And then once we find a good element, right? Once we find a good pivot, basically, the problem space reduces by a quarter, based on the algorithm we define in class. Okay. Okay. So to be honest, this is the only problem I have on randomized algorithms. I could not find or think of others. But if you guys have more questions on randomized algorithms that you want me to talk about after, we can definitely do it. For now, we're going to go into computability theory. Okay, we're going to do computability theory.
Hi. Okay, yeah, so I'm gonna go over computability theory. This year, I'm pretty sure it's not as big of a theme as it has been in past years because you guys have been focusing on randomized algorithms. So don't expect to see too many I guess computability theory questions on your exam. But I guess we're going over it anyways. So a Turing machine is essentially a finite state machine. That also has I guess a tape, right? That represents the memory that it can write to and read from. So if you remember from 2800, you guys talked about NFA and DFAs. It's pretty similar to that, except in addition to that, you now also have I guess a tape header and a tape, and then your transition function also tells you how to move your tape header on certain inputs, right? So I guess informally, a Turing machine is sort of a model of computation. I don't know if you learned about the Church-Turing thesis in class, but I guess any sort of model of computation that we know about can be represented by a Turing machine. And then there's also, I guess, the language of a Turing machine, right? Which is the set of all, I guess, strings that are accepted by the Turing machine. So let P be the property of some group of strings, right? So in this case, I guess P can be more formally defined as the subset of your alphabet star, right? The Kleene star from 2800, and that sort of defines the set of strings that your Turing machine M should accept, right? And that language is decidable, or P is decidable, right? If there exists a total Turing machine that accepts all inputs, that accepts all language strings in the language, right? So and the total Turing machine is a Turing machine that halts on all inputs. So for instance, if we have, I guess this is an example of a language. So the language of all strings that have odd length, right? So would be the subset of sigma star that the length of the string is odd. Yeah. So a language is semi-decidable if there exists a Turing machine that halts on all yes instances of the language. So let's say I give it some string that's in the language, then the Turing machine must halt and produce yes. But if I give it some string that is not in the language, then the Turing machine might halt and say no, but it might also just loop forever. And looping means just it doesn't halt. And all decidable problems are semi-decidable, and this is because given any total Turing machine that decides some language L, you can use that total Turing machine to semi-decide that language as well. So, yeah, it's a Venn diagram. Yeah.
If a Turing machine has defined function, transition function for all inputs, does that mean it only loops if the length of the string being inputted is infinite?
No, you can think of a Turing machine that ignores its input and then just loops. So in that case, no matter what input, like even if you give it a finite input, right, it'll loop. Yeah. So like the state machine can like cycle. Okay. I think it's just vocab. Yeah. So like you can call a language, or I guess you can call a language recursive if there exists a total Turing machine, M, such that the language of M is that language. Yeah. So just saying a language is decidable is the same as saying the language is recursive. Yeah. And then recursively enumerable is the same as saying something is semi-decidable.
Are these like familiar terms to you guys? I'm not entirely sure what you covered.
No. Wait, how?
The last 5 minutes of one lecture.
Okay, who went to lecture and wants to respond?
It was like a lecture, but it wasn't well.
Okay, wait, do you want me to explain? Okay, yeah, I can slow down if you guys want me to. Wait. Okay. Wait, which part is confusing? Wait, which part would people like more clarification on? Yeah.
Can we just go over what was on the last slide and this slide?
Oh, sure. So this is just saying that it's just defining the term recursive, and a recursive language is the same as a decidable language. It's just a different word for it. Yeah, that's pretty much it.
What is it called?
I don't know. Turing named it. I don't know. Any other questions? Oh yeah.
Which set are we talking about specifically?
So a set, I guess it's like the language. A language is a set of strings, right? That is a subset of, I guess, your alphabet star, right? So it can be any. It's just a subset of anything, any strings in your universe of possible strings. Oh, go back. Halting problem. Yeah. So, did you guys cover the halting problem in class? So yeah, just a quick refresher. The halting problem given is like asks whether given a Turing machine M and an input X, whether or not I guess that halting machine, the Turing machine M halts on X, right? So intuitively, it makes sense that the halting problem is at least semi-decidable, right? Because you can, I guess, sort of run the Turing machine M on input X, and if it halts, right, then you can accept. And if it loops, then you don't know, like whether, like you don't know whether or not it'll like eventually accept or not. So you can't like reject or accept the string. Yeah. Oh, and the halting problem is also undecidable, and you can prove that like by diagonalization.
If it's not like the like that you decided to machine type such that like the language of M equals X. So is it saying like the language of the string machine equals exactly X? Like with is a core thing inside?
No, it has to be exactly X. So the language of a machine is the set of strings that the machine M accepts.
Okay, wait, so what happens if like it's more than X?
Then it's not a machine that like decides or semi-decides that language. Right? It's just they're just uncorrelated.
Oh,
right. But you can't like have a machine that solves the problem like some of the time, right? Like, you want it to solve the problem correctly all the time.
okay, so this is like having like a larger language with X thing, like you solve
The language is the set of strings that the Turing machine accepts, right? And pretty much you want to determine whether or not a given string is in the language, right? Does that make sense?
This is a definition. These are not like contrasting sets. We define the language. The set of strings that the Turing machine accepts.
Oh, okay.
It's decidable, not just
Oh, and generally, so a language is decidable, right? If there exists a total Turing machine, right? So a Turing machine that halts on all inputs, right? That either accepts the string if it's in the language or rejects the string if it's not in the language, right? And then a semi-decidable language is one that there exists a Turing machine, right? Not necessarily total, right? That accepts all strings in the language, right? So let's say I have some string like X that is not in the language, right? Then my Turing machine may or may not halt on that. But if it does halt, it must reject the language, reject the string. more questions? Alright, so I guess we have some practice problems. X is the set of all strings that describe a Turing machine that loops on the string 11111. Is that semi-decidable or decidable or not semi-decidable or not decidable? I'll give you some time to think about it. All right. Do people have any ideas on how to do this? The first question, at least. Any ideas? Yeah. Why?
Because anything that's supposed to accept, it'll loop on it, right?
It's actually a little bit stronger than being undecidable.
Semi-decidable.
Yeah, it's not semi-decidable, right? And I don't know if you guys learned about this in class, but there's a problem called the co-HP, right? The complement of the halting problem, right? Which is the set of all strings, of all like machines and inputs, such that the machine M does not halt on input X, right? And that is not semi-decidable because sort of like if you run M on X, right? Before, to semi-decide the halting problem, you just see if it halts, right? But now you can't like wait until like it finishes looping, right? Because it doesn't finish like looping. That's the whole point. Until like you like accept or reject, right? So here, if you like feed in the string 11111 to X, to the machine described by X, right? Then like if it loops, right? Then you don't know like when to stop the machine that like is checking whether or not it loops, right? So sort of like there's no way to even semi-decide this problem.
What's the difference between undecidable and not semi-decidable?
So, not semi-decidable, or I went over what not decidable means, right? There doesn't exist a total Turing machine, that decides the language, right? And not semi-decidable means there exists like no Turing machine, like whether total or not, that decides the language. Something can be. Yeah, there you go.
Can only live in this diagram. Like, you cannot be any combination that's not in this diagram.
Yeah, but like those are the things you would reject, right? So like if it halts, right, then you reject that string. Right? But like semi-decidability is asking like it's about like strings that are accepted. Right? So the strings that are accepted are loop forever, but there's no way to check whether or not that string loops forever because like you have to wait until the loop finishes, right, before you return.
Try to work through the rest of the problem, then we'll reconvene in class on it.
Want to accept it if it loops.
Oh, is that it? Oh, yeah, yeah.
That's gonna be awesome. You live by university. Yeah. Excellent. So, want to check this? It's just like it involves waiting for the loop to finish. Right. So if it does loop, right, then you won't know because it would have just kept going. Right. So you just you like detect the string that
All right, we're gonna go over the questions now. Yeah. Does anyone have an idea for how to do question 2? Yeah.
Semi-decidable.
Why?
Because all the strings, and if you find one string that's accepted, you can just call.
Yeah.
Otherwise, you have to go through all the strings, and then you wouldn't know that it's like it would just instantly loop because you have to go through all the strings where all the strings could not be accepted.
Yeah, exactly, right? So for those people who didn't hear, the idea is you would sort of simulate like the Turing machine X on input 1, right? And then you would do it on 1, 1, 1, 1, 1, 1, 1 until you accept at least one of them, right? And then once you've accepted at least one of them, you can stop, right? And then you can accept. But if if none of the strings in that set, if X accepts none of the strings in that set, you'll never know because you have to keep trying strings because there's infinitely many of them. Yeah.
Let's suppose that there's one string that gets accepted, which is 1, 1, 1, 1, 1. How do we know that the Turing machine will even terminate on the first 4 inputs? How do we know that it will terminate in the instance that it rejects before it finds what it accepts?
Oh, okay. So, yeah, that's actually a really good point. So, what I said before about like simulating one at a time isn't actually correct. So, you would have to actually simulate one, like I guess you simulate the first step of like it on 1, right? And then you simulate the first step of it on 1, 1, and then you would simulate another step on 1, and you sort of do it in a like diagonal pattern. So, if there exists some input, right, such that X accepts it, then you'll find it eventually. Right, so you simulate sort of like one step at a time on each one. Yeah. You would have to prove it formally by reduction. You would have to reduce the halting problem to it, and I don't think that's in the scope of like this version of algo, so I won't go over it. Yeah. Yeah, are we good on question 2? Question 3. Ideas? Anyone want to offer a solution? Yeah. Yeah, exactly. Right. You just run it, but you have to wait for 2 strings to be accepted. And then question 4 is pretty obvious. You just sort of like, I guess, you can just count the number of characters in the string, and then if it's even, you accept. If it's odd, then you reject. The 5th one. Any ideas? Yeah. Oh, the string is there's no like infinitely length string. Yeah. There's a fixed size of the string. So you give it a string, you like go through it. Okay. Wait, does anyone have ideas on question 5? Yeah.
You know that you'd have to to check all n numbers to make sure that it only accepts exactly one of them, because it could always accept some other one for some larger n. So you can't check that it's a yes instant in any case.
Yeah, exactly, right? So before, like for the question 2, right, that was semi-decidable, because once you saw one string you could accept, but for this one, even if you see one string, you can't accept right away, because you have to check the rest of the set, which is infinite, like to make sure that there's exactly one, so there's no more strings that accept, right? And it would take, I guess, like infinite amount of time to check all the strings in the set, so it's not semi-decidable. And then the last one, yeah.
I have a question for the last one. What if we find two that are like two elements that are in this set? Couldn't we just reject?
That's not the case for all.
Yeah.
Might go forever. It's gonna be fine.
Like there might be special cases where like you can accept it, but you can't decide a Turing machine that like works on all cases.
Wait, sorry, why is 2 also on the side?
2? I mean, I guess the intuition is that you would have to, if like none of the strings are acceptable, are accepted, you have to go on forever. Yeah.
I don't really understand like the last one. Like, can you explain like what the?
Wait, like this one?
Yeah.
I haven't gone over it yet.
Oh, sorry.
But would anyone like to offer a solution? Yeah, back there.
Simulate the machine on the input.
So can you speak up?
Simulate the machine on that like given, and then on the number of steps you're doing. You're under 111.
Yeah, exactly, right? So what you do is you take Turing machine X, you simulate it for exactly 111 steps, and if it's halted before then accept, and if it doesn't halt, then reject. Yeah.
If it runs in finite time, does that mean it's decidable?
So wait, can you? So a Turing machine is total, right? If it runs in finite time on all inputs. Yeah.
I understand how you can like say that something. It's easy to prove to myself that something is semi-decidable, but to say that it's undecidable, it's like I feel like I'm relying on intuition that isn't. Like I don't know how to prove that something's actually undecidable.
Yeah, we didn't teach. It was not taught in the course. In past semesters it was covered. This semester it wasn't, as far as I'm aware. But the process like involves reduction from the halting problem, right? So the idea is like if you can reduce the halting problem to some language, right? That means if you can decide that language, then you can decide the halting problem, right? So, and then to show that something is not semi-decidable, you can reduce from co-HP, the co-halting problem, right? And then if I guess the language that you reduce to is like semi-decidable, then that means the co-halting problem would have to be decidable.
So then it's kind of unreasonable to be asked this type of question on the test, right? Because you don't like you know that it's undecidable. We have really done that. Semi-decidable seems really difficult, but undecidable.
I can't speculate to what on the test or not because I have not seen it. But yeah, that makes sense. Semi-decidable. Yeah. That's not undecidable, it's decidable. Yeah, it's in the diagram.
Can we exactly the entire lecture?
Yeah. So we're gonna go over one more example. Maybe this will satisfy you a little bit on like I guess sort of how to prove like whether or not a problem is decidable or not. So we're gonna talk about live variable analysis. This is a problem that comes up a lot in compilers, right? So it's whether or not like a variable is I guess like useful at a certain point. So here, yeah. So here we have a. It's used to compute the value of b, right? So it's considered live, right? But once we compute b, right? After this line here, we don't use b anymore, so it's considered dead, right? Because even if you like delete b, delete the value of b, like it doesn't matter anymore because you never use it again, right? So the problem of computing whether or not, I guess, yeah. So the problem is whether or not. Oh yeah. The problem is we want to compute at each line of code, right? Like what variables are alive. Yeah, I guess which variables are alive. Yeah. So yeah, you guys think that live variable analysis is decidable? me some time to think about it.
Whether or not the variable is and they're asking you.
What they have, they don't know.
Yeah, I think I'll go over it right now. Ideas? You guys think it's decidable or undecidable? Anyone? There's a 50% chance of getting it right. It's just yes. Yeah?
Is it undecidable?
Yeah, why do you think it's undecidable?
If you have like wall true and like x like plus equals 1, you'd always need the value of x.
Not exactly. In that case, x would be live at every program point, right? Because you need the value of x at every step of your program. But that is a good idea. Yeah. So it is undecidable. And to see why, we can look at this simple program, right? So we define x to be some int, right? And then we run some subroutine f, right? And you can think of like programs and methods of programs to be like Turing machines that take in inputs and then write their output on the tape, right? So, and then we return x, right? So the question is x live, right? And if f is an infinite loop, right? Then x is never used, right? Because you never get to this line of code, return x, right? So x is dead, right? But if f actually does halt, right? Then x is live, right? So the process of determining whether or not a variable is live or dead, right, precisely, requires you to know whether or not, these subroutines in the middle, halt or don't halt, right? And that would involve solving the halting problem, which proved in lecture that you can't.
We don't expect you guys to grasp all the nuances of this topic. There will not. What's the? How this?
Yeah, so you can encode your program as a bit string, right? and then you can encode the variable you're interested as a bit string and the program point you're interested as a bit string, and then output yes or no. Yeah. Yeah.
Know whether something is decidable or not, but you like to think about the Turing machine that you're gonna construct for it.
Sorry, can you say that louder?
Like decide whether the problem is decidable or not. Must be considered like the Turing machine that you have to construct.
Yeah, so if you want to show that a language is decidable, you would usually just construct a Turing machine, like proof by construction, right? You construct a Turing machine that's total, and its language must be the language that you're interested in, right? But for like to show whether or not it's undecidable, it involves either proof by like diagonalization, right? Or you can prove it by reduction from the halting problem, right? Which is essentially what we just did. So like solving, in that case, solving live variable analysis would tell us whether or not like the subroutine F halts or not. Right, so that's I guess like a reduction, right, from the halting problem to live variable.
By construct, like to show that's decidable.
Yeah, because if you give an example of a Turing machine that is total and decides the language, right, then you've shown that the language is decidable.
How would you reason about it without creating a if it's like a short answer, you're not going to create the Turing machine.
You can create a Turing. I mean, you can argue about what the Turing machine would do, right, and you can argue that each step halts. Yeah. I think so, yeah, because if it does halt, right, then you would be able to see whether or not the variable is live or dead.
Okay. Oh god. Okay, we're gonna go over dynamic programming now. Hopefully should be more familiar than computability theory. Okay, so again, the key idea is you're gonna have this really large problem. You're gonna break it into sub-problems. It's typically very similar to your original problem. And then you're going to store the solutions to those sub-problems so you can easily access them and build up to an overall solution for your original problem. Yeah, so you're going to build larger and larger sub-problems. Okay, you're going to always have a base case when you have DP problems, obviously. It's going to be your smallest sub-problem that you're going to build up from. You're going to have a recurrence relation, which is going to outline how you use those sub-problems in order to find the solution for a bigger problem, because that's why we're storing them in the first place. And then memoization, which is storing the sub-problems somewhere that we can access it relatively quickly, constant time or whatever. Okay, any questions about key ideas of DP? Okay. Okay, yeah, so sometimes it can get kind of confusing going top down versus bottom up. So top down is what you guys are familiar with as like recursion, which is you start with the biggest problem, and you're eventually going to recurse on the problem until it gets really, really small. Then once you get down to the smallest sub problem, you go back up the call stack and you just solve your original problem. So that's top down when you start with the big problem, and then bottom up is going to be you start with the smallest cases first. So that's like DP. You start with your smallest sub problems. You eventually build up to your bigger sub problems. And those results are stored along the way. Okay, so does that make sense, everyone? The difference between top down and bottom up. Cool. All right. So solving DP problems is very formulaic. You start off by defining what your sub-problem is going to be. So how you're going to break down your original problem into those smaller sub-problems. You're going to write down a recurrence, something that I highly recommend when you guys are doing your final. It makes it a lot easier to grade if you can like actually write out what your recurrence relation is somewhere. Like maybe if your recurrence relations can get pretty long, right? Like it can be like opt ij equals max ij less whatever. It's gonna get really long. And if you want to use your recurrence relation in your algorithm, but you don't want to like write it all out, you can just write that your recurrence relation above, and that's just gonna make it a little bit easier for us to parse through. But you don't have to do that. But you're going to have some sort of recurrence that uses those smaller subproblems in order to get the solution to the bigger problem. You're going to clearly state how the subproblems are being built up, and that's pretty important too. Is Are you going to just keep, incrementing one on one of the variables, or how are you basically building up those subproblems to get to your overall solution? Because sometimes it's not exactly intuitive. How you're going to recover the answer. So this is really important too, because a lot of times the algorithm will be asking you for maybe like an optimal pairing, but your recurrence relation is maybe finding the minimum of something, and that's not what we want. So we don't want you to just return like the minimum that you find using your subproblems. You actually have to be able to backtrack, find the pairings that got you to that minimum, and then output that. So when we be really careful when it's a DP problem about what we're asking you to output, and if that does include backtracking, to include that in your algorithm. It's like easy points if you get the recurrence relation correct. And then proof of correctness and runtime analysis. So proof of correctness is going to be pretty much, it's going to be inductive. And it should follow pretty naturally if your recurrence relation is correct. And then runtime analysis, again, should be pretty straightforward. Okay, let's do a problem. So you have an online interactive textbook with n activities. Each activity I has a level AI and then a point value PI. And both those are non-negative. So once you complete activity I, you can get PI points. Yeah, but only if you haven't completed any earlier activities of level AI or higher. So to formulate that, we're basically wanting to choose whatever activities are going to give us the most points, with the constraint that any activity that happens after the activity that we're currently on can't have a level that's below the activity that we're currently on. That's gonna make more sense in the next slide. Yeah, so you want to design a polynomial algorithm that gives you the maximum amount of points possible. Does everyone understand that problem statement? So it's asking us, what is it? It's asking us to output what? Points, yeah, okay. So do you want to do the next? Oh, is the solution on the next slide? Oh, okay. Yeah, we'll give you time to go through. Well, it doesn't have like that graph that is like. Yeah. Okay. So just to make it a little clearer, so you have these 5 activities, and I is indicating what activity number it is. AI is going to indicate the level. The PI indicates the points. So for example, if you chose 1, 3, that's fine, but you can't do 1, 3, 5 because 5 comes after 3, but 5's level is before 3's. Okay, so that's kind of what the constraint is. That can be kind of confusing. Okay. So, yeah.
So you have to do the activities in increasing order of index I.
Yeah. You can't switch around the order. Okay, so go ahead and try your best to write a recurrence relation for this. Yeah, we'll give you a couple minutes.
So it's like
Okay, did anybody find a recurrence relation for this problem that they want to share with everyone? Yep.
Off of I comma n is equal to the max of pi plus of I minus n, or I minus 1 n minus 1, or of the I minus 1 comma n.
What is n and what is I?
N is the number of activities, I is the activity you're on. Or n is the number of activities like your max.
That's close. Wait, so opt n I. Where can I see it? So I would just be curious about how you would bake the constraints into here. About like activity level and or like the activity and the points.
Aren't you just increment or because once you're at like activity I, you're only looking at the activity like the optimal from I minus 1.
Right.
So another.
But you wouldn't you have to like check? We'll go over the solution. That's close. Yeah, that's close. You would have to be checking a little bit more. So you only actually need one variable for this one. So we don't need to be creating subproblems based on the size. So the way we would do it is basically opt I, where I is going to be the activity number. We're going to add the point value to the maximum of opt j. And j is going to be all of the elements in the opt array where such that j is less than I and the level of j is also less than the level of I. Okay. And in order to do this correctly, we need to create some sort of like dummy activity so that we don't get weird numbers with this dummy activity 0, which is specified up here, where there's no points or anything like that, so we won't pick it. But even if we do, we can just take it out. But that's kind of what our recurrence relation would look like. So we do need to be testing or checking the optimal value for all j that's less than I, and the activity level is also less than I. Does this recurrence relation make sense to people? Yeah, so it can be kind of confusing because I think a lot of times, at least for me, my instinct is to also use two variables, and like one of them should be like the number and decrease subproblems based off of that. But in this case, we only need one, and we just need to be checking the activity numbers that come before I. Okay, yeah, so to implement this, it's pretty simple. You're just going to be computing it in order of I from I to n. Yep, do you have a question?
Doesn't this assume that you pick the I element when you have like optimally you're already taking the last element since you're adding pi?
Yes. And then you check the maximum.
So yeah, so that's not the complete answer. So you're gonna have to this is your final step.
Okay.
So your final step is going to be taking the maximum value. Yep.
Would it also be fine to just do the max of that opt I you have there and whatever opt n I minus 1 is? Basically saying it's either I is going to be included in it or not.
Yeah, that'd be fine too. Yeah, that'd be fine. Okay, so runtime is O of n squared. We have O of n subproblems. And for each of them, it's just linear time to try to find the best optimal thing to add it to. And then your proof of correctness is going to be induction. You're going to use your recurrence relation in order to prove that if it holds for, like I minus 1, it holds for I. Should be pretty straightforward. Does anyone have any questions about this problem or DP in general? Do you want to do that? Yep. Okay. I have to go.
So another pretty simple but elegant solution to this problem is that you can reduce the shortest path. I think I harped on this at the first review session too, but to solve DP problems, reducing the shortest path is usually a very solid way to go because it abstracts away any reasoning about actual recurrence relations and you just need to make a graph. And so now that you've done a crap ton of graph problems in the last couple of units as well, hopefully you're really comfortable with this. But the idea is that you just pick a node for every, index I, right? And you'll have that same like 0 like starting node. And for all j from 1 to n, you'll have a node that goes from j to n plus 1. So you'll basically have every node goes to the ending node. And then the start node also goes to every other node, right? And you can always go to nodes sequentially such that they're ahead of you and the activity levels are increasing. So you basically just model every path, right? Every possibility in this graph. And you can use Bellman-Ford to find the minimum cost path, right? And the idea is that we put negative costs on the edges because we want to find a maximum, but Bellman-Ford gives us a minimum cost path. And so by just taking the negation, we'll get the maximum profit basically using this reduction. Yeah.
Like AI is less than AJ, not BJ.
Yeah, my bad. So I think there's a good number of problems on your practice problem set for the final that can be solved also via reduction to shortest path. So if you're not super comfortable with it, I practice it because it does come a lot more naturally, to me at least, than deriving a recurrent relation from scratch. Does everyone understand this alternate solution though? Okay. Yeah. Yeah, you create the edge if you can take those two activities sequentially, right? Yeah.
Could you also reduce this to project selection?
Project selection. As in, like, you model like sequences of activities as prerequisites?
Yeah.
Maybe. I'm not sure. That seems like a lot more effort, though. Yeah. Okay. This next DP problem is much harder, so I'll give you some time with it. So this is shortest path with a set of bad edges. So you're given a directed graph G with n nodes and m edges, costs on each of the edges, and a subset of the edges are bad edges, right? Indicating some sense of danger when you use them, or whatever danger means in the context of this problem. And given some integer k is less than or equal to n and two nodes s and t, you would like to find the minimum cost path using up to k bad edges. So give a polynomial time algorithm that returns the minimum cost of an ST path using n most k edges. This one is much harder, so I will give you more time to think about it.
Don't use bad edge. Change the number of bad edge. So you have to, and it's not like I'm home. That's the point though. It's like free time. My mentality
All right, so let's go through this problem. And you can start. So Here we're gonna need a three-dimensional recurrence, right? So opt of VIL is gonna be the minimum cost path from S to V using at most I edges, of which at most L are bad. Okay, so if you recall the recurrence relation from Bellman-Ford all the way back many lectures ago, it was opt of VI, which is the min cost VT path or SV path using at most I edges. This is the same with just a third parameter L, which defines how many forbidden edges we're allowed to use. And so the base case, opt of V00 is just 0 if V is equal to S, right? But it's infinity for all others. And that makes sense, right? Because we can't get from B to T using like 0 edges, right? Okay. This is a recurrence that we're going to use to compute opt of VIL. So it'll be the minimum of opt of VIL and opt of VIL minus 1, and the min over all WV in R. I think that should be in F. Cost of E plus opt of VI minus 1, L minus 1. This is saying take your forbidden edge and consider the case where you have one less edge, or take a non-forbidden edge and consider the case where you have one less edge but same number of forbidden edges. Yeah?
Where in the original problem did it say we were constrained by the number of edges we could take from S to T? I don't really remember that. Now there's like the bad limit, but did it ever say?
I mean, you aren't, but this is how Bellman-Ford's recurrence is derived, right? Bellman-Ford gives you an ST path, and it's built up using a SV path with at most I edges. You're not limited in the number of edges you can use, but Bellman-Ford uses that when it's constructing an ST path.
Why is opt VIL already populated? Or is it like populated as infinity?
I think it's, I don't think that should be in there.
Okay. So like that should be removed. And then the second one is opt VIL minus 1. Should that not be in there either?
No, this should be in there. This?
Yeah, why is that in there?
Because it's one less forbidden edge, right?
One less. Yeah, but isn't that the
No, but even like you might not take it, right? But you still need to consider the case where you had one less forbidden edge.
Okay. Should be one less edge. Or one less like right? You can usually use the same like
Okay, so the order in which you update, you go from 1 to n minus 1, and for a given I, you'll go from L equals 1 all the way up to the min of I and K, right? If K comes before I, then you'll stop there, and if I comes before K, then you'll go until I, right? And you'll return the opt of T using minus 1 edges, right? So observe that an ST path will take at most n minus 1 edges, and K being the number of total forbidden edges. And then the running time of this algorithm is O of n cubed K. So other questions about this? I know this is a little confusing. Yeah.
In the first part of the recurrence, like the first thing inside the min, like isn't OPT VIL? Isn't that what you're trying to find?
Yeah, I don't think that should be there. That's a typo.
Okay.
Yeah, right. So this case, I mean, really the two important cases are these, right? This is I am using a forbidden edge. This is I am just using an edge that's not forbidden, right? Oh, R is a set of forbidden edges. It should be F. And then E is a set of just total edges. Yeah.
Instead of not being there, should the first term be opt to be I minus 1?
I think so. Yeah. It should follow the exact same template as Bellman-Ford does in the book. But I think the solution for this is a bit outdated. Yeah.
Those like two like bottom recurrences B and W.
That also makes more sense. Yeah. Okay. I'm not sure why my solution to this was so fucked up, but I will go back and fix it before.
You got it wrong on the prelim.
I did get it wrong on the final, yeah. But the actual solution to this problem is also not very well explained. Yeah. Also, what did I do? Okay, so before we move on to NP completeness, are there any questions on DP in general? Yeah, I will go back and polish this before I post the slide. That's my bad. But hopefully the question is at least good exercise. Like it is a more complicated, DP problem. No? Okay. All right, so let's talk about NP completeness. Yeah, what's your question?
Could you just use, since like the nasty guys are all positive, could you use extra with like the adding that like after going on as
No, you cannot. Because Bellman-Ford is not able to tell you, or Dijkstra's is not able to tell you like if it used a forbidden edge or not, right? So if you tried it, you'd have to try it on like all the paths that exist from S to T, which could be possibly exponential, right? So like, yeah, you can't just like run Bellman-Ford or Dijkstra's as a subroutine inside of the DP algorithm and expect it to like give you enough information back about the number of forbidden edges you've used. Does that make sense? All right, so NP completeness proofs. I'm not going to go over the whole like what is P, what is NP. I'm hoping at this point in the course you've gotten those big questions settled. So really, I just want to go over the steps of the proof again. So I saw a surprising number of backward reductions on the prelim, which is, maybe not so great. So remember, when we're trying to show that a problem is NP complete, we need to choose some problem we already know is NP complete and reduce it to the problem we're trying to show is NP complete, right? And I think some people internalize that like in their head and said, oh, like, yeah, this is a direction that the arrow needs to point. But then some people like wrote the right direction and still wrote a backward reduction anyways, right? And so remember, what you're trying to do is like, you have to start from an instance of the problem that you already know is hard and create an instance of the problem you're trying to show is hard, right? So for example, if you try to make a graph out of the inputs to the weighted multiple interval scheduling problem on the prelim, that would be a backwards reduction, right? Because you're not making a graph, right? You're given a graph and you're trying to make jobs and intervals such that they only overlap if the sets have an independent set, right? So that's really important. Just like, please make sure that like on the final, like you do not get your reduction backwards because it is worth a lot of points, and getting your reduction backwards will basically guarantee you like less than half the points of the problem. Right? But so the 5 steps that we need to do to show that a problem is NP complete. Also, I like how I also graded a lot of problems that like use this exact framework. Like some people even like wrote like 1 bubble, 2 bubble, 3 bubble, 4 bubble, 5 bubble, right? So you need to show that the problem is in NP. I didn't see very many problems with this at all. So you just need to construct some polynomial time verifier. You also need to design some reduction that goes from some NP complete problem to the problem you're trying to show is hard. And so that means you need to pick your NP complete problem carefully. And we'll again go over kind of how to do that. The reduction has to take polynomial time. So another issue with the backwards reductions is that some of you guys did not give polynomial time backwards reductions, right? Because if you made a graph with a node for every like weight value, for example, well, those weight values might be specified as integers, and if W is 1,000, then you need to make 1,000 nodes, and so it's not polynomial at that point; it's pseudo-polynomial, right? So your reduction does need to be polynomial time, and then you need to prove the yes implies yes in both directions, right? So a yes instance of independent set implies a yes instance of WMIS, and vice versa. Right? So is everyone solid on like the foundations of how to show a problem as NP complete? Good. Okay. So. Oh, that's good. I'll have a shorter. Okay, so choosing a problem to reduce from, right? We have these like categories of problems that should hopefully kind of guide you. I think a lot of people on the prelim also got misled into thinking it was subset sum because there were like WIs, right? But the real giveaway is that like there's an at least constraint, right? And the at least constraint should kind of signal in your head independent set is a good one to go with, right? So packing problems, right? These problems that have like, oh, I need to pick a set with at least k nodes or at least k items, right? That's a good instance of using independent set, or click is like the set variant of independent set if you want to think about that way. Problems where you need to cover a set, right? I need to pick a minimal set of nodes that spans the whole graph, right? So has at most k in the wording, probably a vertex cover problem, right? I think if you know independent set and vertex cover, you're pretty solid on most of them. You should also hopefully know sat reductions. I don't think that there would be, outside of this list, there's definitely not anything that you would see that like you wouldn't be able to solve with things on this list, right? Sequencing problems, so if there's like a sequence of decisions to be made, you can usually model that as a Hamiltonian cycle or a Hamiltonian path. And then numerical problems, so if there actually is like a numerical flavoring to the problem where I need a sum of a bunch of elements, you might be able to model that as subset sum. Yeah. Does anyone have more questions about like how to choose a problem? Because I realize that that's a very like high level framework, and sometimes it can still be hard to identify the right problem. Question.
Is there ever
They're usually interchangeable.
It's usually easier.
Yeah. Okay. Yeah. So this is basically what I just said, right? If you're unsure of what to go with, try SAT or 3SAT. Okay. Yeah. So this problem, yeah.
We know that like NSAT, like for your grader is NP complete, right? So if for whatever reason it seemed like it'd be easier to use that, but we don't know for sure if it's approved in the textbook or not for like some higher or whatever.
I would recommend not using it just because, but like generally there's no reason to, right?
Like if you really need to and you can't think of a way to do it, do that, then sure. But like, yeah, try to use 3SAT.
Yeah. I think it was proved in some. Was it proved in lecture?
I think you might have touched on it. Right? Like,
Okay. If you covered it in lecture, then it's fine. It's fair game. Yeah, but then it's like unfair to people who aren't here, right? Sure, fine. We can use it. Yeah, that's fine. Yeah. You need to pick some n greater than 3. I would question why you need to pick some n greater than 3 and like think really carefully about like, oh, is there a need to use like 6SAT versus 3SAT, right? But yeah. Okay. So this problem is the half Hamiltonian cycle problem. So you're given a directed graph with n vertices and m edges, and you need to decide, does there exist a simple cycle that contains at least half the edges in the graph, right? There's some formal notations there, and you want to prove that's NP complete. Yeah, I'll give you a little bit of time to think about it.
One of them is way easier.
That's a great marker.
I remember in lecture, I remember it was I also remember it was a crazy graph. Remember, it was like a graphic. It's like the other graph. And the thing is, like, I wrote up one of the you love it. I like that.
All right. Oh, that's loud. Any ideas? Yeah.
Newtonian cycle by like taking the input graph and then putting disconnected copies of the graph next to each other.
Yeah, I think that works. Yeah, that works. Yeah, so just to repeat what you said, you take the graph that so you reduce from Hamiltonian cycle, right? And you take the input graph, you duplicate it, and then you run half ham cycle on it, right? So if there exists a half ham cycle on the graph, then that half ham cycle must be a ham cycle on one of the two graphs that you created, right? So just take that half ham cycle and take the cycle that you get from there and apply it to the graph that you just got, or the original graph. Yeah. You can also create like n disconnected nodes. It's the same idea, right? Because the ham cycle or the half ham cycle can't go through those nodes. So any half ham cycle you get would have to go through the nodes in the original graph. Yeah.
But if it's at least over 2 nodes, can't you just like add nothing? It'll still be a hashtag cycle.
No, because like the argument is like if you create one additional node, right, or like no additional nodes, well, you can't.
No, you can add nothing.
Yeah. You can add one node. Oh, so you can't even add one. Like you have to add at least n over n nodes because like think about the case where you have a disconnected graph, right? Right. If you have a disconnected graph, so like let's say my input to ham cycle G has like one node that's like disjoint, right? Then the I add additional node, right? And I try to find a half ham cycle, right? Then I would find a ham cycle that goes over like non-disjoint parts of the original graph. Right.
In your reduction, what if like in this 2 disjoint graphs you have like an n over 4 ham cycle here, another like n over 4 cycle here, so in total.
But they're disjoint, so they can't be connected. Yeah. Any more questions? Yeah.
A ham cycle.
A ham cycle and a simple cycle. A ham cycle is a graph that like is a cycle that goes to every node exactly once. A simple cycle that goes to a node exactly once. Yeah.
Is all of n plus n polynomial? It's like a general question.
Yeah, it's polynomial because you have n edges and nodes and m edges, right? So yeah.
Create the new graph on the side. That just complexity of n plus m, or
Yeah. So if you create n disjoint nodes, it's O of n. If you duplicate the graph, it's n plus m. Yeah. Yeah.
instance we would have m edges and m edges and 2 n nodes.
Yeah, this is one of those like dumb reductions, right? It's like kind of like double stat, if you remember that from the last practice review session. But I mean, you're basically just like forcing, forcing a yes instance of the Hamiltonian cycle by just adding a bunch of arbitrary nodes that are disconnected, right? That's the easiest way to do it. Okay, so this problem is significantly harder, so I will give you some time to think about it. But I think it's good because I don't know if you guys have seen reductions like this, so I don't know. I think it's an interesting one. So the idea is that you have some like communication network, and it's modeled by an undirected graph, and there are K users, and they're interested in using this network. So you kind of like send a request to some pair SI to TI, and you want to make sure that you can accept all of these requests only if there are disjoint paths P1 to PK. Yeah, such that they share no nodes, right? So more formally, we state this as a path selection problem. So it has some input G and some set of pairs of nodes, S1T1, S2T2, up through SKTK, where G is an undirected graph on n nodes, and S1 to SK and T1 to TK are distinct nodes in V. And so the answer is yes, if and only if there exist paths PI between SI and TI for all I from 1 to K, right? And such that none of those paths share any nodes. Does that make sense? Does the problem statement make sense?
Is T and S disjoint?
Yes, they're all disjoint. Disjoint nodes in G. Like T is not S, right? Like S and T are disjoint for all, for all S and all T. Okay. So let me give you a hint because this one's hard. So let me go next slide. Okay. The hint is to try using SAT or 3SAT to do this, right? So here's like a partial construction that you can kind of start off with. So for each clause and each variable, add in SI-TI pair. And for the variable xi, SI-TI pair, you want to construct your graph to have two possible paths, right? One going through all the true nodes, one going through all, two possible paths. One representing the variable being set to true, and one being representing the variable being set to false, right? And there may be, some number of intermediate nodes that define those paths, right? Remember, we start with 3SAT, and we reduce to path selection, so we have some CNF, right? And we want to know, what does our graph need to make this construction correct, right? So really, we're asking how many of the nodes do we need on those intermediate paths that go on those ST paths for each variable? And also, what about the clause paths? How do we define those? Okay. So take some time to think about this or to try and get somewhat of a construction working. It is a pretty tough problem, but I'll be around asking questions as well. Would it be easier to see the hint or the problem?
Was the heinous DP question actually on test? Did anyone get it right?
I really like a main over instead of max.
Yes.
All right. Did anyone come up with a partial construction or a full construction even? For problems like this, it helps to draw. If no one has any ideas, I mean, I could give you guys more time, or we could just kind of go into it. What do you guys prefer? More time? Okay, I'll give you guys some more time.
Can you go back to the
What do you mean any preset? Like any queue? Any queue. Like any. Yeah. You just like use that. How you prove it? You have a construction. All right, so I want to have enough time to get through the last few questions and also just stick around afterwards and not be here, for super long. So here's a construction. Yeah. Okay. So we're gonna let X be sat. You could also make it 3 sat. It doesn't really matter. Given an input phi, let n be the number of variables and m be the number of clauses. And you want to create an input with n plus m pairs, right? So we have an SITI for each variable and an SITI for each clause. For each variable pair, there's exactly 2 paths in G that connect them. And one corresponds to the variable being set to true, and the other one corresponds to the variable being set to false. This is all given in a hint, right? The paths connecting SI to TI will have m intermediate nodes, where m is a number of clauses. And let the intermediate nodes corresponding to XI being false be VXI CJ, right, where CJ is like some clause number, and the ones corresponding to being true be VXI bar CJ. Okay? Next slide. Now for each clause CJ, so now our notation is getting a little heavy here, but we have a clause pair SJ prime to TJ prime that needs to be connected. So if CJ has KJ literals, there will be KJ paths of length 2 in G connecting the clause pair. Right? And so if XI appears in CJ, G will have edges SJ prime B. Blah, blah, blah. The intuition, right, is that you have a path. You have exactly two paths connecting from the clause nodes to the variable paths. Okay, so there's an SITI, right, and there is exactly one edge that goes, or sorry, there's an SJTJ which represents a clause, right? There's exactly one edge that goes from the start clause node into one of the paths of the variable that would set it equal to true. That would set the clause equal to true, basically, right? And then there's another edge that goes from that same variable to the sink of the clause path, right? And you do this for all the variables in the clause that would satisfy the clause, right? I'm gonna let that sink for a second. Yeah.
Can you draw it for us? Look like
I did not have time to make a picture. My bad.
you on the blackboard.
Maybe after. Yeah. Yeah, I can definitely draw this out for people after. Yeah. This was a past homework question. Yeah. Yeah. No, I mean, it's definitely a hard question, right? I mean, I think it becomes more reasonable with a hint. Yeah.
We also do it in like a slightly different way, where we create like, so for every clause, and let's say it's that, we create like, we create
Two nodes and add what?
an edge between those two nodes. So that'll be our path.
I think that just like trivially satisfies the constraints, right?
Right, but like we could, I was thinking that we could just
Sorry, I can't really hear you that well. Maybe after the session we talk about it. Okay, so let me hopefully try and paint a picture in your head, right? So each variable has an S and a T, right? And between those S and T, there are two paths. Guys, keep quiet down in front. There is an S and a T, and there are two paths that go from S to T. And along those paths are M nodes on each path, right? Which represents the number of clauses, okay? There are also nodes connecting to those paths from the clause nodes, right? Because each clause has an S and a T, right? And so for every variable in the clause, it will connect to its corresponding like knot, right? The idea is that if I set xi to true, the false path is open, which means that the clause that contains some xi can take the false path to then get its own disjoint path, right? So that's the intuition, right? Like that's why you can always, like that's why we have two paths for every variable, right? Because whatever path is not being used is used for the clause that relies on that variable to be satisfied, right? Because each clause only needs exactly one variable to be satisfied, right? Or one variable set to true to be satisfied. Does that make sense? Kind of. Yeah. I don't know how to get this up. I mean. Yeah, I mean, okay. If you are interested in seeing the full reduction after I get through the rest of the questions, I can come back and go through it for those of you who want to stay after. I promise you the exam question will not be this hard, but yeah, I'll also post, like I can post an image of this or of what this will look like when I have some more time. Really, I kind of wanted to show you like an interesting three-step reduction. That was kind of the idea of this one. Three-step reductions are hard. Like we had one of them on one of the homeworks, and it was pretty tough. So like step reductions in general are not very easy. Oh, and yeah, so I mean, here's the proof, right? The proof basically just explains how you can recover the paths given the assignment. And given the past, how you can recover the assignment, right? You basically force disjoint paths, right? But like, if there exists disjoint paths for the clauses, guys, if there exists disjoint paths, you can always just take the literals being set to whatever value like the clause paths didn't use, right? And that must be a satisfying assignment because of the fact that you had enough disjoint paths. Right? Okay, so now I just have a crap ton of true false, and so I thought we could go through them, and then we'll probably finish before 9, which is good because then I can have time to just answer for like questions, and I'll just do like office hours for another like 30 minutes. Okay, so here's a Gale Shapley true false question. Given n hospitals and n residents, there always exists unique stable matching. How many people think true? How many people think false? Good. We'll see the answer after we go through the first 3. So the consensus was true. I might draw these up somewhere to tally the correct ones, right? Okay. Suppose we have a decision problem L that is NP complete. Then there must exist a total Turing machine M that accepts exactly the inputs that are yes instances of L and rejects the inputs that are no instances of L. How many people think true? How many people think false? Why do people think true? Yeah?
It's in NP, so you have poly times verifier.
What about false? Anyone have a reason? Just doesn't sound right. Okay, the consensus was false, I think, so we'll see. And then, like the consensus among the crowd was false. Right? Oh, really? Okay. Let G equal V be a flow network with every edge E assigned some capacity, and let AB be a minimum cut. Now consider a new flow network, G prime, with every edge having +1. Is AB still a minimum cut of G prime? Who says true? Who says false? Can I go to the next slide? Okay, so maybe we would benefit from some review of earlier topics in the course. So for the first one, can someone tell me why it's false? Yeah? It's not unique, right? There can exist many stable matchings. Gale Shapley just finds a specific one.
Yeah, and you can find another one by running it with like split,
right?
like split proposal.
Okay. What about the second one? So someone had the right intuition here, right? It's in NP, which means there exists a verifier, right? This TM just describes a verifier. And then the last one is false. Yeah. Maybe we do. Interesting. Okay, I have some more, so don't worry. Redemption arc. Yeah.
Like a simple example.
The last one. I can draw one out after. Yeah. Okay. The Gale Shapley algorithm, with hospitals proposing, will match each resident to their first choice. False. Okay. Next. Consider a divide and conquer algorithm that solves a problem of size n by solving 2 problems of size n over 2. It takes O of 1 time to combine the results from the subproblems. The running time of this algorithm is O of log n. Given a graph G with n nodes and m small edges, small vertex cover asks whether there is a vertex cover of size at most 2. Small vertex cover is NP hard because vertex cover can be reduced to small vertex cover. How many people say false? How many people say true? Okay, so they're all false, right? So it was better on that one. The second one is O of n. So the recurrence would be 2t n over 2 plus O of 1. And if you unroll that recurrence, you'll get 2 to the log 2n, which is just O of n. It's two. You have two subproblems. You sum over two. Okay, one more. So, in a flow graph containing more than one minimum ST cut, a maximum flow will saturate at least one of them, but might not saturate all of them. True or false? How many people say true? How many people say false? Kind of evenly split. Okay, next question. The problem of determining whether a flow graph has an ST cut with capacity less than K is in CoNP. Do people recall what CoNP is?
Never happened.
It was. This was awesome.
It's never been since each other.
Okay. Well, this is just a fun problem. Does anyone know or care to venture an answer? Okay, so CoNP is a set of decision problems that can be efficiently refuted, right? So you can say no, basically, but you might not be able to say yes, right? So it's like, given some certificate or some refutation, you have some algorithm that can determine that it's a no instance. So is this problem? What do you guys think? True, false? False? Okay. And what about the last one? P is a subset of NP. True?
No.
It is absolutely, yeah. Alright. So it turns out the second problem is in CoNP. And the first one is false. So it does saturate every ST cut, right? Like the definition of a minimum cut is that all the edges crossing from A to B are fully saturated. So every single ST cut satisfies that property. Right? Okay, so that's it. Thank you guys. This was a long review session. I will stick around. Thank you. I'll stick around for a little bit, but yeah, good luck studying. I got